Hi, this is probably the last episode of Concept Map on topic E, and it actually took longer time than I expected, so I hope you find it useful and enjoy it. If you haven't watched the previous 4 concept map on the other topics, please refer to the playlist and I'll recommend you to go in the order that I created the map. And so without further ado, let's just start from here. So, nuclear and quantum physics. Let's start with the notation, okay, which I'm sure you all know, and then the idea of isotope. Very self-explanatory. Here I put an example of what isotope is. So, hydrogen 1, 2, and 3. And all these 3, although they basically are all hydrogen, they are, of course, again, isotopes, and each of them, they are called different nuclei. So there are 3 nuclei in this diagram. Okay, so I hope you know what that means. And that will mean it's a specific type of atom or nucleus that is characterized by the proton number and neutron number. So as long as that number is different, then it's a different nuclei. Okay, and then when we talk about isotope, then we certainly will talk about the stability. For example, the hydrogen 2 and 3 are not stable, and therefore they would then eventually become hydrogen 1. There's a diagram that you sort of need to recall in terms of the stability of it, and you also need to know how to read it. And you might be shown on how they may have different decay, alpha, beta, and gamma, etc. And then you can see one thing that for the line that is neutron equal to proton number is somewhat below what is actually happening. So in the reality, if you try to really look at it very closely, we will need more neutron than proton, right? Just take a look for a few seconds. Okay, so that is the usual ratio, okay, having more neutron than proton to make it stable, okay, not 1-to-1 ratio. Anyway, okay, so these are the different decay you must have heard, and probably something new compared to maybe middle school is you now have beta minus and beta plus decayed. And so the equation, like here, allow me to just have this hand drawn, and you need to know alpha is basically a helium nucleus, that's 4-2, okay, with 2 plus, and then beta minus and beta plus is like this, 0, -1, and 0, +1. And they both go with a neutrino. One is anti-neutrino for the negative, or the beta minus, or the neutrino go with the beta plus. I would say you more like have to memorize it, unfortunately. Okay, in the older syllabus, then we go deeper into something more. So in your case, I think it's just the best to just memorize it. The last thing is the gamma, okay, and the gamma is just a photon. It doesn't come with any proton and neutron, therefore the number is 0, 0 if you really want to write it, okay, or you just don't write it, is also fine. Okay, the star on the left, it means that it's at the excited state, and therefore on the right you can see the same element or same nuclei basically. Without the star, it means that it's more on the relaxed state. The other thing that you also can see from my hand drawing here, other than just balancing the equation, which is very essential skills, you also see the word discrete energy and continuous energy. So alpha and gamma are discrete, so whenever they release it, it will be of a very definite values of energy. It will vary, of course, so you can have multiple different discrete energy, okay, but it's not like continuous, okay. So the continuous one is for beta plus and beta minus. And in fact, the idea of the measurement of measuring it to be continuous led to the discovery, okay, that's why I put the word discovery of neutrino, okay, because when people try to measure it, they find, oh, okay, somehow it's higher, lower, and it's strange because like where does the missing energy coming from, and where does the missing momentum coming from? And so the neutrino is actually later discovered, okay, although they are really hard to detect because they don't interact much with the matter. Here is another chart that you are expected to know how to read. In fact, it's quite simple. I think you just do it by logic, you could already do it. Okay, on one side is neutron number, on the other side is atomic number, which means the proton number. So you can see alpha decay, it will -2 for both. Beta plus or minus, then will change accordingly. Okay, so essentially if you understand this, then you should be able to understand this. It's just that you need to know this is the way we illustrate how the decay may happen, change from one nuclei to another nuclei, or maybe the element as well. The other diagram that you may get to see is called the energy level diagram. As I said, the alpha decay will be of a discrete energy, but they might be of a different discrete energy. So as you can see here, as an example really, 4.6 and 4.8 mega eV. Okay, so then they both would decay from radium to radon, and then for the one with less energy in alpha, then they can further emit another gamma. Okay, so this is a diagram that you need to know how to read and simply, okay, to know about how the representation could be. Okay, I forgot to put the thumbs. Okay, thumbs. Okay, moving on. Okay, talking about alpha, beta, gamma, then we must talk about the ionization ability. So it's something to do with the energy that they carry, because they basically are giving their energy to the nearby medium, for example, the air. Okay, the ionize, that means they rip off the electrons, so that require energy. And so alpha takes the more energies, and therefore they are very good at ionizing, versus gamma will be very least energy, and so they could still ionize, but not as much. And this is also the reason why alpha was sort of being consumed. Okay, don't use this word, but the idea was, I think it's easy to understand. It will be consumed very soon, and therefore they cannot penetrate far. Okay, and while for gamma, because they don't really, use those energy much, and therefore they can penetrate through much longer distance, and therefore the penetration ability will be the reverse. You also need to know, according to the syllabus, to know some application examples. So here I just put down some very popular application, alpha, beta, gamma, and if you are not really knowing them, then just Google or AI just to get to know more. Okay, basically for each of these applications, they use it as a way to probably detect something or measuring something as a probe, etc. Okay, so I'm not going to cover it in detail here. Going back a little bit, when we talk about the general idea of alpha, beta, gamma, these are radioactive decay, and the property of them is they are random and spontaneous. These are very specific physics terminology, okay? And so you might be asked to explain what they mean. And so it's not a word that you can just randomly make up. So the word random, it means that it's not like they are unpredictable. That's wrong. The better way to understand it is, it means that the reaction, okay, or radioactive decay, is by probability. So that will mean that in the next decay, let's say you have a certain percentage of the chance that you may decay or not decay. Okay, it's like you flip a coin. Okay, whether or not 50% is head, 50% is tail. So that's probability. So in the long run, or in the larger population, you would then know how much they perform, okay, in terms of decay or not, whether or not they're head or tail. For one of them, yes, it's hard to predict because your population is so small. So then you think it's random, but in a bigger size, then it's not, okay, it's by probability. We still call it random. In terms of spontaneous, it means it's just happened naturally, but at the same time, I would say more importantly, compared to chemical reaction, because these actually are nuclear reaction, okay, and they are different. Okay, alpha, beta, gamma are nuclear reaction, while chemical reaction, the behavior or the properties are different. Chemical reaction could be like respiration, photosynthesis, you learn. Okay, even if you don't learn about, don't study biology and chemistry, you should know these, at least these two, right? And you know that they would also be affected by things like pH value and then temperature, for example, and other things. But for nuclear reaction, interestingly, they do not, okay, change the rate by having different temperature or pressure. And this is actually interesting because this is how there are things like carbon-14 work. Okay, if you don't know what carbon-14 is, then go Google yourself. Okay, basically how the archaeologists try to, take the dinosaur bone, for example, and then try to check the radioactivity of it. Then we can then check how long time ago, okay, it's been decayed, and it's good because then imagine the variation of temperature and pressure. We cannot trace, of course. It's been billions of years. So interestingly, we can actually manipulate this property and then help us to find out how old the stuff are. And then, of course, we will then talk about the activity and calm rate in terms of measuring how fast they are decaying. And these two words, activity and calm rate, are different. It's similar, but it's different. Okay, so that's why we have two names. Okay, again, these are actual terminology, although activity is like a very general English term. So the idea of this, okay, is basically listed out here. I think you don't actually need to know this detail, but the basic idea is the activity is just really how fast the source is decaying itself, while calm rate is more like in the lab, you measure it. So the measurement may be offset by systematic error, background, radiation, and other things, while the activity is the true value, basically. And of course, not to mention about the tech may have efficiency issue or maybe directional issue and other things. Okay, just to illustrate you the idea and then have the impression that they are different. Okay, so we talk about background radiation because in the outer space or maybe in the surrounding, you have other things that emit radiation. Anyway, so in the end, people are very interested to know about their half-life. As I said, half-life is an indicator to show how fast they decayed. And as well as just now we mentioned carbon-14, for example. So for SL student, then you need to know how to calculate half-life by simply dividing 2, okay, counting really. And then for HL, then you need to know all these equations. Okay, I think you probably should know. And then you need to know how to handle the math on exponential function, of course. And then need to know the decay constant meaning as well. So the lambda is a decay constant. Okay, I think you can read the sentence here by yourself. All right, so that should be it for this area. All right, so now going back to more like the square one, you might be thinking about the emission spectrum, the E equal to HF thing. I'll come back to this later. I would like to go for the binding energy actually. Okay, so one big thing, binding energy. Okay, the reason why we have nuclear power, nuclear weapon nowadays, okay, because of this. And then an idea that closely related is mass defect. So these two are the definition, basically. You can refer to the wording. By the way, I also make a terminology list I talk about in another video. So if you haven't checked that, then you may want to check that. Okay, I think that may be easier to just have a whole list of everything at once. The idea of binding energy, okay, the reason why you have that energy is because the existence of strong nuclear force. Okay, so SL, you also need to know about this word and the idea of it. The strong nuclear force, it only happens when it gets really close. So close that we are talking about the scale of the nucleus of an atom. So it will only act on the proton and neutron, basically. And this is the reason why the proton will not repel due to the electromagnetic force. Imagine they are positive, so they should repel. And they are not. I mean, I'm here, you are here, and we are forming a certain atom of iron or whatever, and they don't, always repel itself in the nucleus. So there must be a force that hold them together. So here comes the strong nuclear force. Okay, again, they are attractive, okay, because we are holding them together, the proton, and of course together with neutron, and it's also short range. Okay, so unlike the electromagnetic force, which is basically infinite distance, same as the gravitational force, infinite distance, this one only works in short range. And so, of course, you know about the E equal to mc squared equation for calculating the binding energy together with mass defect. Just one thing to remind you, when you calculate it, the mass usually are provided in the unit of U, which is called the atomic mass unit. And you can see the definition here. And the most important thing I would say is you need to know the conversion, so then it's easier for your calculation. Otherwise, you take so long time and you might be making careless mistake. So on your data booklet, you should be able to find this. Okay, just go to look for yourself. 1U, okay, whenever you have a mass of 1U is probably somewhat between equivalent to 1 proton, 1 neutron, okay, although you should not take it as 1, you have, again, the exact mass of proton and neutron you should use in terms of U, okay, it's 1.0 something, okay, in your data booklet. But when you have find out the mass defect in the unit of U, then you can simply multiply by 931.5, and then the answer you get is simply in MegaeV. Already. You will see the unit have C -2 because that is going to cancel out in the equation of the C square. And that's why it's so convenient. You can just multiply this and get the answer in MegaeV. Okay. In terms of what U exactly is again a unit that scientists make up for the conveniency and also easier representation. And so we take U as like almost like around 1 proton and 1 neutron mass, and we take it by looking at how a carbon-12, because carbon-12 is very abundant in the world, and also it has 6 protons and 6 neutrons, so probably I guess the scientists took that as a way to define it. Okay, so 1/12, that means kind of like the average, okay, of proton and neutron. Okay, and so that's the idea of binding energy. And moving on, of course, we have to talk about the idea of binding energy per nucleon. So if you have calculated the binding energy of an atom, that if you split all of the neutron and proton by itself, then of course you can obtain the binding energy if you know the mass defect. And then if you divide it by the number of nucleon, that means proton and neutron numbers, then you can obtain the value of binding energy per nucleon. And imagine the scientists put all these together. So this is not one experiment, but many experiments put together as a result. And so this is the graph that we have. Okay, it's a very important graph that you, again, have to recall directly in your mind. And then you need to remember the shape. Okay, it's pretty much like that. So the features of this, okay, by the way, you must remember that the y-axis is average binding energy per nucleon, okay, per nucleon is important. And then on the x-axis is just the nucleon number. So the features of this is first, okay, you have the peak of nickel and iron, okay, either way is fine, okay, different textbooks have a different saying, but they are more or less the same. The second thing is they start from 0, 0. Okay, 0, 0 means is the hydrogen 1 is the very first element we have, because hydrogen is only having 1 proton. So come on, you can't split it. So that's why it has 0 binding energy to start with. Actually, I don't think I'm right. It shouldn't be 0, 0. It should actually be 0, 1, 0. Okay, my bad. Okay, so because the x-axis is 1, so 1, 0 instead. And then we also have the spike, although I don't think IB Physics would ask you about it, okay, but you do see that there's spike at helium and carbon and oxygen. Yeah, these are more like just exceptions, okay, you don't really, unless you are very interested, then you go and check out why, but these are just exceptions. But generally, you can see the trend is like it goes really steep at first, and then peak at nickel, iron, and then going down. Okay, and then for the later one, after iron, you can see that the range is stay within around 7 to 9 MegaeV. So something that you actually are expected to know. The other thing that, in fact, as a consequence of this, okay, so we talk about the features. The consequence of this is then, if you are looking at how you can get energy from a nuclear reaction, you surely would know about fusion and fission, okay, for sure. Then remember one thing, that this graph actually helps you to identify when you should do the fusion or when you should do the fission in order to get energy. Okay, we are talking about that. We assume you want to get energy from it. We can actually do the reverse, but that's very complicated. So for sure that as iron and nickel is like the boundary, okay, at the way that you do the cutoff. The thing on the left, you should do fusion, so then the binding energy will increase after you combine them. Okay, so I think this is something you have to maybe remember. Okay, so when they go up, you get energy. So same idea on the right hand side for example, uranium. When you split them, it go from here to somewhere higher. Of course, you are not going to split beyond iron. Okay, not anything smaller than iron. So again, the binding energy will increase, and this is how you get energy. So going up, okay, is to give you energy in the nuclear reaction. So pretty much here, okay. And so continuing on the fission idea, you again need to know there are two kinds of fission. One is spontaneous, one is neutron-induced. In fact, the idea of spontaneous fission is simply what we just mentioned about alpha, beta, and gamma. Okay, so you sort of need to know, okay, there are two kinds, but in fact, you already know about it. Okay, alpha, beta, gamma, they are called the spontaneous fission because they also split to something smaller, isn't it? The other one that is, in fact, more people will often talk about when they talk about fission is the neutron-induced one. Okay, so the uranium, of course, okay, the very popular one. And so you must have seen, okay, this uranium reaction. Okay, so it's so typical that you almost have seen it a lot of time. I deliberately express it in a way that is 235 uranium plus 1 neutron become 236 first. It's actually important to know that the neutron is being captured within the uranium, and uranium become 236, and then the 236 become unstable because of that, and then it split into the later daughter nucleus and 3 neutron. Okay, so it's not like again, I always told my student when I was a student, I always simply think it's more like a very mechanical thing that you flow a neutron to 235 uranium and then it just split. No, it's not like you shoot a bullet to something and then it split and explode. No, okay, it's actually, it does capture it and then it become unstable, and then that's how the fission happened, and then the energy released. So this is forming you a chain reaction because you can have 3 neutron afterwards, so you gain actually 2 neutron by doing this, and so these 2 neutrons can continue to react with the other uranium-235. And because of what I talk about in terms of capturing, then the process of this, okay, having neutron to induce a process cannot be too fast. Okay, the neutron speed cannot be too fast. So imagine you have the nucleus here, the neutron just go, okay. And then normally if you go slow, then yes, okay, capture. But then if you go so quickly, then it's like you have a magnet, you throw a paper clip to it, okay, it cannot capture because it's going too fast. Okay, but if you flow at the right speed, of course not too slow, okay, then it can capture. So then the reaction can happen. Regardless, it's not easy, of course, to maintain the reaction rate at the way we want, and therefore we must introduce some devices. So these are the name: control rod, moderator, heat exchanger, and shielding for different purposes. So you can just refer to this. If you're not sure, then perhaps read the textbook or find more information to check. And lastly, whenever you build a nuclear reactor, there's always some sort of waste you have to manage because they are radioactive. And so there are 2 kinds. Okay, it's a very new thing that you have in this syllabus. It's called the low risk and high risk waste management. The simple idea is if it's high risk, that means it's super radioactive, then different countries would decide to put them with a lot of thick lead, for example, and put it really deep underground, okay, so that it won't be affecting, people on the ground and the residents, of course. For the low risk one, for example, the worker, maybe they have the jacket, they have the shoes, then for those, then they probably would, get it, it's not very high highly radioactive, then probably they will just lay it off with the soil, etc. Okay, I think it's just really general idea about it. I don't think they would ask you in a very deep detail. So we are done with fission, and let's go back a bit to talk about fusion. Okay, and so fusion associated with astrophysics in our new course. And so let's look at maybe the example of fusion first, okay, which is the one happening in the sun. And I believe this is something that you also are expected to sort of know. I mean, I don't think you have to recite the whole equation at all, but you at least have to know it comes from hydrogen 1. So 2 hydrogen 1, this is a sequence, okay? So the first one is 2 hydrogen 1 fused together, and then they become hydrogen 2, okay, and these things, and then a hydrogen 1 and a hydrogen 2 would then be combining, okay, fused together, become helium 3, and then helium 3 with another helium 3 will combine, become helium 4, okay, and 2 hydrogen 1. So the whole process is like the game 2046. Okay, you have played before, and then of course throughout the process, because it's nuclear fusion, then they will release energy. Okay, going back to the chart here. So that's why a lot of energy released in the sun. Then when we talk about the sun, then of course in order to make the fusion possible, we will require the whole system to have high density and high temperature. So imagine the sun basically is just a lot of hydrogen 1. It has to be really packed, so high density, so then they really are forced to go together. Imagine if you have hydrogen 1 and hydrogen 1, they basically would like to repel each other normally. So you really have to push them together, okay, so then you can fuse, and therefore you require high temperature, because then one and another will be of very high speed, and basically they are colliding. It's like a car crash, basically. They can't even stop themselves. So high density, high temperature is the requirement, and in order to make the star stable, or considering their stability and size, then we have to consider these two things. Okay, so a star, the reason why they are this big, okay, why not they become bigger or smaller, is due to two things. One is going out, one is going in. So the one that pushing them, making them bigger, is called the outward thermal pressure. Basically, is the idea of fusion itself, how the energy is released, and therefore they try to expand. Okay, they want to go out because of this thermal pressure. The other thing that keep them towards each other, okay, going inward, is the gravitational pressure, because I mean they are mass, okay, so they want to attract to each other. Of course, it doesn't really, you can't really feel it by, okay, I stay with my friend and we attract each other gravitationally, but in terms of this big scale, then they do. Okay, so this is the reason how the stars can be maintained stable, and the size of it, or whether or not they become unstable and becoming bigger or smaller. Now, another thing that we often talk about in terms of the star is the luminosity, L. So in your data booklet, you have that equation. We talk about it in topic B, I believe. And then essentially it's equivalent to radiated power. So how the radiation power, literally power as in energy over time, okay, is being measured and quantified. And so it will lead us to another term called brightness, which is the intensity. Intensity is equal to power over area. Area as in the virtual sphere. Again, I have explained it in the topic B in the last video, so you can go and check it out again, or do a bit of research if you don't get it. But basically, luminosity or power is due to the star, or itself, how the temperature is. I mean the equation you can refer to, the surface area, emissivity, etc. It is what it is, okay, luminosity. But for brightness, it depends on your distance, how far away you are from it. So a star can be really high luminosity, but it doesn't really look as bright because you're really far away from it, okay, or the other way around. So the one we actually measure as a raw data, you may imagine is brightness or intensity. Together with the distance, then we can work out their luminosity. And so therefore, measuring the distance is very important, and therefore we also introduce the concept of measuring distance by using the concept of parallax. And so here is an equation, here's a diagram you can refer to. So the star you want to measure has to be sort of close. It can't be too far, of course, because you are basically relying how the stars have a parallax movement at different time. Okay, you can see in this diagram, while at the back there are some background stars which appear not to be moving over time. Okay, and so then you can find out the parallax angle and then have this geometry to work out the distance. You probably will be provided with this diagram, okay, or the idea of this, or the angle itself, and then you can calculate the distance using the equation. However, you might need to use this conversion, okay? So I simply screen cap this from data booklet. Just make sure that you know how to convert from one to another, okay? Light year, parsecond, AU, etc. AU is simply the Earth-Sun distance, just so you know. Now let's get back a bit to look at the 𝐥𝐶 diagram. So since we have the luminosity, we have probably somehow got the temperature and also the radius of them, radius as in the size of the stars itself, then we will be able to produce a 𝐥𝐶 diagram. So after many years of scientists' effort, everyone's contribution, then we can produce a graph like this called 𝐥𝐶 diagram. So one thing that you need to pay attention is first is luminosity against temperature, okay, is in log scale, and then the other thing is temperature is in a reverse scale also. So the x-axis is temperature, but on the left is hotter, on the right is colder. Then you also need to know how the radius is also drawn, okay, so you can see the diagonal line here in this diagram. So they may not provide you the full detail of the diagram. They may ask you to identify different groups or expect you to know shifting up and down like that. It will have different radius, etc. So sun is sort of here in the middle, okay, with about 6,000 K temperature, and of course its radius is 1 solar radius because it is the definition itself. And so the luminosity is also at 1 solar, as again this is a definition. So along this you can see it's a main sequence stars, okay, and then here we have the supergiant and red giant at the top, and then we also have the white dwarf here, okay. So the white dwarf is the one with really low luminosity but really high temperature, because then they have experienced a lot of things and they are really hot. It's just it takes time for them to cool down, okay, and they do not take fusion reaction anymore, okay, and that's why it's also be seen as the dead star, because they don't do anything anymore, okay. And so the evolve of how different things may change is also expected to know, okay. And so I believe this is all for astro. If you have anything to add, please let me know. Now we go back to something earlier about emission spectrum and quantum physics. So first, okay, I'll cover the SL part first, is about the emission and absorption spectrum, which scientists first find is very interesting, because how can you expect that happen? So for different elements, they will show you a different emission and absorption spectrum. Basically, it's just a composite of each other. And so it's very unique for each element because they have different energy level, and we also find the energy level is discrete, and that's why we can produce a diagram, okay, like this. We talk about the very ground state, which they usually are staying at, and then the excited state, we have different order, and if you somehow can overcome all of them, then this is ionization level. That means you can then rip off the electron from that particular atom. And so the energy difference is calculated by this equation, E equal to HF, and so high frequency, high energy. So and also this thing go in both ways. So if they are excited, when they go down, they will release a photon, and that's why you see those emission spectrum line with a very specific wavelength for color. It can also go up, okay, if you provide them with, again, the exact photon they need, and then they can jump to that particular level. You cannot have any random number, okay, because it's discrete. So it's like climbing a ladder. You have to have the exact value. You can't have like somewhat in between the two ladder steps. And so they can absorb, they can release, okay, and the process of maintaining the excitation is not long, okay, so they very soon will get the excited and release the energy. You can see some dotted line here. I just want to address, okay, the connection to other topics. So in terms of emission and absorption spectrum, you can see here, okay, for those in HL only, is related to the diffraction grating we talk about. Because imagine the light coming from the star is, again, combined, okay, or simply if you have and certain element got excited with high voltage. The color you see, neon light, for example, is like pink in color. So how can you identify and disintegrate the color into different strand is, again, thanks to the idea and power of diffraction grating. So you might have this come together and then being asked, okay, so even if you have a very close blue line, so the blue, the pale blue, the dark blue come together, you can still identify them with a certain power of diffraction grating. The second thing that I also want to talk about is for this emission spectrum is also closely related to the thing we talk about in Doppler's effect. So if you remember, we talk about the redshift, how scientists try to measure the spectrum coming from, all around us in the universe. Most of them are showing a redshift. Okay, when we talk about redshift, it means that in the emission spectrum, it goes towards the red side. And so the consequence or the conclusion of this is that the stars, most of them are going away from us. Okay, so that's a very interesting and very strange thing actually. How can you imagine everything is leaving us, okay, while we are moving in a certain direction? So that leads us to the idea of universe expansion, okay, one of the mainstream theory nowadays in physics. So I hope you can make that connection and also appreciate the physics. The very last thing for SL student is that you need to know about Rutherford experiment, which is the very famous gold foil experiment. We also could call them the Geiger-Marsden experiment because these two gentlemen, they are basically the student of Rutherford. Okay, the student actually did the experiment. Rutherford was their professor. So either way, okay, the name is quite popular, or the gold foil experiment. Anyway, so just some key ideas to recall for this experiment is you shoot the alpha source, okay, a helium nucleus to the gold foil, really thin foil, one layer thick, okay, in one atom layer thick in theory, okay, and so we do expect they will bounce off, but in fact the result telling us that most of the alpha just penetrate through. Many of them did not even deflect. Some of them deflected, yes, but behind it, very few will get measure in front of this gold foil. So that means they are reflected basically. So the numerical result telling us that the atom is actually mostly empty. So imagine the way you can only explain what happened from this result is the atom is mostly empty. And you only have the nucleus very concentrated at the middle, and the nucleus is positive. Okay, so they already knew alpha is positive, and that's how when they reflected, then they know the nucleus is also positive. So this is what we learned, okay, from this Rutherford experiment. So I guess we only are left with HL stuff, and let's continue with this trend after Rutherford. So it's not exactly the Rutherford experiment, but imagine you also have something, say, positive, okay, shooting towards the nucleus, okay, And we do expect, of course, they might be repelling, okay? However, at a really high energy, we find something really strange, okay? That beyond a certain energies, okay, the prediction versus the actual one is going actually much lower, okay? And so it's something to do with the fact that at a high energy, it gets so close, because imagine one would have a head-on collision, okay, and then bounce off because of electromagnetic force. And that's, you can then easily model it by using the energy equation, half mv squared equals to electrical potential energy KQ1, Q2 over R. That's a prediction. But then, what happens is, when you get too fast, it gets to the range of strong nuclear force. And so this equation does not consider the strong nuclear force. And so what happens is that when the strong nuclear force in place, then basically some of the atoms or particles are being absorbed by the nucleus, and therefore, okay, the measurement will be very off from the prediction, because the prediction is only made by using electromagnetic force. And so that's the interesting thing, okay? So it also helps us to find out a way to estimate the radius of the nucleus, because as we said, the strong nuclear force is only effective near the proximity of nucleus, and so this helps us to measure, okay, the nucleus itself. And so there's an equation that we find out, in fact, they have a certain relationship in terms of their atomic number A, okay, versus the radius. Our log is the Fermi radius, which is a constant, okay, found by a scientist Fermi, of course. And the consequence of this, so interestingly, is that it says all nucleus density are actually the same. And so no matter you're having hydrogen or uranium, their density are actually the same. Okay, we're talking about their nucleus, not the atom. Now let's go back to something related to the energy level. So I'm sure you know, eventually we will get to have an equation, okay, of this, which can predict, okay, very interestingly, okay, the one that we have for hydrogen. We actually work out a way to predict the energy level, and it matched so well with the experimental result, okay? So normally we work out with the experimental, okay, data, and then work out the energy level, like a reverse engineering. But this one, okay, going from the fundamental law of physics, then we actually can predict when n equals to 1, 2, 3, 4, what happened to the energy level. Again, it matched with the empirical data. And it started from Bohr's model, okay, considering how a hydrogen atom is like, having one proton in the middle and then an orbit, okay, a circular motion basically by the electron. And so he hypothesized that there was a quantization of angular momentum. So that means that the angular momentum of it would be of a discrete value. And the idea of it is not easy to understand, of course, okay? But what you may associate the idea with it is, imagine the electrons are not really orbiting, but being as the standing wave, okay? And if you, again, have explored yourself with more advanced physics, you heard about that's the quantum physics itself. That electron is not really orbiting, okay, but it may be here, there, Schrödinger's wave function you may have heard about. It was in the old syllabus, you don't need to know them anymore. But the idea of being as a standing wave, okay, in the orbit is actually quite essential, and I think that link closely to what you learn in angular momentum in A4 and also standing wave in C4. Okay, and so I think you need to have an idea of this picture. And therefore, okay, we can have an expression of angular momentum. Okay, mv is linear momentum times r is angular, equals to the end multiple of h over 2 pi. And so with this, interestingly, I mean, it's a hypothesis, okay, we are not really sure that this is true or not, but then it really allows us to get to the result of this. And so it really makes us to accept, okay, yeah, probably, okay, the angular momentum is quantized, okay, because it just matched so well. Now the very last thing is in here, starting from photoelectric effect. And this is a setup. Okay, I think you need to know and recall the setup. So you have a light, we can perhaps at a certain intensity, at a certain frequency or wavelength like UV, purple or even red color, and then we'll find that the purple or UV light usually would allow the electron to be liberated from this photosurface. Okay, photosurface is a kind of metal. There are various kind of metal. You can do that, but they come with a different work function, which we'll talk about later on. And then this electron may be able to go to the other side, and then we can then measure the current of it. And in order to also probe and measure the kinetic energy of it, we use a battery or a certain way to stop them. Okay, so that's why we will talk about stopping voltage, so that we can make some measurement. So the general observation, okay, like I said, is electron will be liberated when light is shown on the photosurface, and it's something really strange we didn't expect. And then more strangely, okay, there are some features that I would recommend you to recall for photoelectric effect. The first thing is the intensity of the incident light does not affect the energy of each electron. So whether or not the electron has a high energy or low energy has nothing to do with intensity. Low intensity, you can still get, okay, a really high kinetic energy of electron. Number two is for each electron, their energy depends on the frequency. Okay, so again, it's not the intensity, but the frequency. Of course, now you know it's something to do with the equation we just talked about, E equal to HF. Okay, so high frequency, high energy. At the same time, there's also a minimum frequency, or we can call threshold frequency, but it's a minimum. Okay, because if you have too low frequency, that means you have too low energy, and therefore it cannot be liberated. Okay, and again, it's not about intensity, it's about frequency, which is not anticipated if we stay with the wave theory. We will eventually suggest that light is behaving like a particle. So that's why we come with the duality. We still accept, okay, light is wave, okay, but at the same time, they might behave like particles. So that's why the duality. Lastly, coming back to the feature, is that the electrons are emitted without time delay. Okay, this may not sound really right to you. I mean, yeah, it just emits. Okay, the main idea is that imagine we still stick with the wave theory. Then imagine the wave is like sending to the photosurface. Then the energy will be accumulated because there's nowhere else that can go. Okay, so maybe after a certain while, it's like you cook. Okay, and then the energy is sufficient, and then it's like boiling water, you may imagine, okay, that it just come out. So it's not something that we have seen, okay. The thing is, with a very low frequency, okay, below the minimum, as we said, no matter how high intensity you use, no matter how long time you are shining the light onto it, it doesn't really emit electron. So it's nothing to do with time. Okay, so again, very strange, okay, and we have to then have this paradigm shift. So in terms of the equation, okay, I'm sure you know this is the equation, and work function, okay, here it is depending on the photosurface only. So different metal, nickel, iron, zinc, okay, they have different work functions. Some of them harder, some of them is easier. Stopping voltage, the battery, okay, we talk about. So stopping voltage is a way that you set the voltage negative, you push the electron back to where they're coming from, and then we always can find when the voltage is of a certain maximum, when the current just barely zero. Okay, that's called the stopping voltage. And because of this, okay, I hope you have done the experiment, then we can then talk about this equation. So EV basically is the energy of that one electron, because they were stopped by this stopping voltage, and therefore you can imagine when they were just liberated from the photosurface, then this is the maximum KE they have. So you have this equation in the data booklet, okay, but you also need to know, okay, this is not in the data booklet, so you need to know how you can express it yourself. I just draw this diagram to help you out, okay, to understand a bit more. So imagine the Bohr is an electron, okay, coming up with a certain kinetic energy, okay. Again, they may have different kinetic energy actually, okay, but we only talk about the maximum one. So the one with the maximum kinetic energy coming out, and then because of the stopping voltage, the battery in reverse, it want to push it back, okay. So it's like the ball rolling up on a slope. The slope, okay, come with the payment of GPE, okay, if we talk about like the usual macroscopic idea. The GPE now is equal to E times Vs, okay, it's energy that we can quantify. And then we expect that the ball, when it roll up, okay, of course it will get slower, and then it just barely reach the top with 0 KE. And basically this is how it happened in the photoelectric effect. So then I hope you can then come up with this equation easily by logic. Now we talk about the minimum frequency, okay? We also have a name called threshold frequency or critical frequency. Again, different textbooks may have different saying, but they are basically referring to the same thing. That is the minimum frequency that you can liberate electron. And why it is minimum? Because it just overcomes the work function. So if you want to express an equation, then yeah, this is the way you can say it. Again, these two, okay, you don't have it on the tablet, so you have to come up by yourself with this idea. Lastly, we talk about the intensity of light. So we all know that the intensity, yes, it does not really affect the energy of each electron liberated. However, it has an effect to the current. Okay, so bear in mind the first thing is the I here referring to the intensity. Intensity is basically power over area, okay? So with greater intensity, you come with greater power. And power is energy over time. And so one thing that in IB physics they expect you to know, interestingly, is that when you do not change the intensity, okay, listen to me carefully. I doesn't change, and therefore P doesn't change. And because it's per unit of time, right? So E doesn't change. Now what happened is this E is referring to the total energy by, say, the lamp you are shining the light, for. And the total energy equals to each photon, HF, times the numbers of photons you have. So the very interesting relationship is that if you somehow can maintain the intensity the same, but you switch the frequency, let's say you switch it to higher, then the number of photons you can emit will be less. Okay, and so that's the interesting interaction between them. If you still don't get it, let me give you a quick number. Okay, I always tell my students. So let's say you have $500. Okay, which is the total energy you have. You can either make it $2 and then times 250 of them. So each of them have $2, okay, and then you can have the quantity of 250 of them, or you can have, let's say, 100, okay, but you can then only have 5. So like imagine the money is like the energy of each photon, and the number behind is how many you can have. So increasing the frequency, increasing the H12, each energy, yes, it will make it easier to liberate the electron, but at the same time, in theory, it will reduce the currents, because the current eventually you can measure depends on how many electrons you can liberate. Okay, so later on we'll look at some diagram. Actually now we'll look at some diagram. So sorry for the space, I can't really cram everything inside, and therefore I have to draw a really long arrow here, okay, branching from the feature. And then I think this is a really good exercise if you could try yourself. Okay, and of course I'll just show it to you here. Remember I just said about how frequency would change the number of, like changing the frequency without changing the intensity will affect the number of photons emitted. And so here's a graph showing you that if we have different frequency, same metal, so same work function, okay, same intensity, what happened, okay, when you have different voltage? Okay, and so at the very beginning, yes, it's the stopping voltage, okay, and after that you start to receive electron. And so for the lower frequency one, okay, you actually will have the most electron, because assuming they can overcome, okay, the work function still, then you have more, okay, going back to the concept I said, okay, and therefore for the higher one, although they have a higher stopping voltage because they are of higher energy, however, you cannot have too many, and therefore the total number of electrons will be less, and therefore the current will be less. Okay, very interesting. And the next thing is, if you only change the intensity while keeping everything else the same, then the idea is very simple. Then it's just the same stopping voltage because the frequency is also the same. And so with high intensity, then it just go higher, okay, for at all time. Number 3 is another graph, KE against frequency. I'm sure you have seen it. Okay, so a quick recap is, let's say you have 3 different metals, then they would then of course have different work function. And then on this graph, very interesting, very elegant thing you can find is on the y-axis is work function. And on the right, you can see I wrote the slope of all 3 lines. They are all h. H is Planck constant, so it's a constant. So that's why you see when I draw these 3 lines, no matter what metals they are parallel because they are of the same slope. Okay, on the x-intercept, you can see I wrote FC, referring to critical frequency. So they will have different critical frequency, again, because they have different work function and therefore different requirement to have the minimum frequency to overcome that work function. Lastly, if you are asked to draw the KE against frequency graph with different intensity, high, mid, low, in fact, because intensity has no effect on the KE of each electron, and therefore it's just one line like this. Okay, so they are all the same in this case. Okay, this would be a very good recap, I guess. Okay, maybe put yourself a test to draw it yourself. Now we have 2 more branches to go. So one is the matter wave, one is Compton scattering. Let's go with matter wave first. So matter wave is suggested by Louis de Broglie and other scientists when Albert Einstein talked about and showed the world about photoelectric effect. And so de Broglie think that, hey, if light can be particle, then maybe everything particle can become wave as well. So that's why we come up with the idea of matter wave. Okay, it's a proper name. And therefore, for anything like a basketball, an electron, they can also be a wave. And this is the equation, okay, which looks very simple. You have it in the data booklet. And so for anything that is of a certain momentum, then you can work out the wavelength for the matter wave. So even you talk about an electron, if they're moving faster, slower, they will be of a different wavelength already. So here is a classic example that I would say you are expected to know. Okay, imagine you have an electron that's been accelerated through a certain potential difference v. So from 0 speed to a certain speed v through the potential difference of v voltage. Okay, and so you can use the equation KE equals to the electrical potential energy you have, and then you can work out the equation of the speed and then plug it back to the momentum, and eventually you'll come up with this equation. Okay, I'll leave it to you as a practice. You do not have this in the data booklet. Okay, and so I would say it's best if you know how to derive it. And then so when you are asked in exam, then you can do it. And it's important because it leads to a very famous experiment of literally just like what I said, you accelerate the electron, okay, so the heated filament can produce electron. It's a very special physics effect, okay, so the electron is produced, but they are just being around, okay, and then they will get accelerated through a certain voltage, okay, and then directed towards this nickel target. So similar to the Go4 experiment, we have a movable detector to detect at what angle, like how the electrons are reflected, etc., or diffracted, etc. And the result is very interesting. Okay, let's look at the result first. So the result is like this. We normally expect that, okay, then maybe just go go like that. But then we strangely find out at a certain voltage, like 54 V, okay, of course it can change, okay, you can use something higher if you really want to, or something maybe lower. Of course not, it can be too low, okay, then you can't see the effect, it has to be a certain high voltage. And so for this one, this particular voltage, the corresponding angle is 50, as in you will see the intensity decrease, which is normal, okay, because the angle is further away, but then it suddenly increases. So how can we explain that? Then it go back to the idea of the Bohr's matter wave, because then now the electron is really acting like a wave, while the nickel, they are having atom nickel here, and then you can see there are gap between them. So this is like the slit. Okay, so it's like, yes, particle acting at the slit, and then the electron coming in as a wave, just like what you learned in the previous chapter. And so we can actually use this equation, n lambda equal to d sine theta. Again, is from, okay, you can see if you see my dotted arrow, you know where it's coming from. Okay, so this is what we learned in wave already, is exactly the same thing. It literally helps us to predict and match with this angle, 50 degree. Okay, that is actually having a constructive interference. Okay, and it's mind-blowing because, I mean, they are electrons still, okay? So how can they somehow have constructive interference? Okay, so this is, again, when you accelerate them fast enough, and this phenomena that they can exhibit, very similar to wave. Very lastly, we get to the Compton scattering. So it's more like additional experiment we have. These provide an additional evidence that light has particle nature. So just very quickly, recall that photoelectric effect does the same. Okay, so it does provide the idea that light behave like particle. Okay, while if you recall earlier in double slit experiment, then yes, Thomas Young, okay, double slit experiment, then that experiment is showing us that light behave like a wave. So of course this comes later, photoelectric effect and Compton scattering comes later. So what happened is if you shoot a photon light basically to an electron, it will scatter off, and the light that you have afterwards will be of an increased wavelength, and that's what, in other words, frequency decrease. Frequency decrease means you have less energy. So what happened to those energy is given to the electron. So why would that mean? What would that mean that it is particle? Because this is exactly what happened to, again, what you learn in terms of conservation of momentum in 2D. I think that is the reason why IB decided in, if you remember in topic A, we talk about, very strangely, very hiddenly, is this a word? Okay, that you have the momentum learned for everyone as a lecture, but the lecture you particularly need to learn about the 2D momentum. Okay, and I believe this is the reason here. Okay, it linked to Compton scattering. Okay, and of course, if you don't really get it, that's, I guess it's okay. You are more like expected to simply apply this equation. So yeah, the change of wavelength, and then something to do with the angle, you know, all these things. So I believe this is all, and I wish you all the best in your studying. If you find this useful, then please leave a comment, tell your friends about it, and that really helps a lot and means a lot to me. I will hope to see you again in the next video.